Hello class, today I will present my final project of ADTA 5900. First we come to the part 1, a time series of data set. The dataset I download from the website is named COVID data, which has recorded the coronavirus 19 source data across all the countries over the world. The data type includes the text data and the numeric data. The whole dataset includes 11,620 records, but here I only want to discuss the subdataset of the United States. This is the downloaded CSV documents in my computer. And this is the Excel file of the subdataset of the United States, which consists of 110 records recording the coronavirus-related data from December 31st last year to April 18th of this year. Then we come to the part 2. The simple RNN with sine wave data. First, I produced the data range and got their sine values as my dataset. Then I split the dataset into 75% training data and the 25% testing data. Then with this dataset, I use time series generator to generate time series benches for training and testing. The length of the input sequence was set as 60 and the bench size was set as 5. Meanwhile, I create a complete simple RNN which consists of 2 subdatasets. The simple RNN layer with 80 neurons and the fully connected forward neuron network layer with 1 output. This is the summary of the simple RNN model. You can see there are 2 layers. And this is the diagram of the simple RNN I drawn in the PowerPoint. Actually, I'm not sure whether it's correct. Then this is the evaluation of the model. From the graphs, we can see the performance is quite good. Then we go to the part 3, the LSTM cell concepts. As we know, the simple RNN has a problem of only having short-term memory due to its vanishing gradient. The long short-term memory neural network concept has been proposed. There are 2 most important concepts: cell state and gates. Cell state can be considered as information transporting channels, and it can carry relevant information throughout the processing of the sequence in the series without reduction. So it can mitigate the problem of short-term memory. For the gate concept, the gate help to regulate the flow of information moving along the path of processing the sequence chain. There are 3 gates for get, input, and output. Each gate is a neural network. It means each gate can learn to decide what information should be kept or not due to its relevance or irrelevance. Then the similarities and the difference. Both cell state and the hidden state can be considered as information transporting channel. For the difference, for the hidden state, the information from previous cell will be weighted or C, the information can be changed. But for the cell state, there is no weight involved with the cell state. Any later time step can use information carried from the previous cell state without any reduction. This is the comparison diagrams. We can see the difference. In the cell state, the line is straight, whereas in the hidden state, the line is not straight. It means the information will be weighted. Then we go to the part 4, the LSTM with the time series data. First, I will introduce my dataset. The S&P 500 is a stock market index that measures the stock performance of 500 large companies listed on stock exchanges in the United States. And many people consider it to be one of the best representations of the U.S. stock market. For this assignment, I choose the S&P 500 data for 3 years, 754 data points as the train and test data set. Then the data from April 16th of last year to April 15th this year, 252 data points as our forecasted data. The design of the LSTM model, there are three LSTM layers and 2 job of the layers, 1 dense layers. And this is the diagram of the neural network. There are 3 LSTM layers, 2 job of layers, 1 dense layers. And this form shows the summary of the core parameters. The percentage of data for testing. There are 3 layers of LSTM. There are 60 neurons in each LSTM layer, and there are 2 job of the layers, and 20% data will be dropped off in the job of layer, and the length of the time series input sequence is 50. There are 20 bunch size for training, and the number of epochs for training is 50. And the evaluation of the model, we can say it's good, not very well, but it's okay. Then began to use the model to forecasting. Use the model to predict the S&P 500 data points for from April 16 of last year to April 15 of this year. The parameters keep the same, or we can see the graphs. In this graph, we have 3 curves. The first curve shows the real value, the close price, the real price. Then the second, the right curve shows the forecasting values. And the third curve shows the error. It means the distance from the forecast to the close. Then we go to the part 5, redesign the neural network. And I would like to improve the network performance through redesigning the neural network and changing parameters of network training and the testing process. Then I hope the neural network can improve its learning ability. This is the summary of the revised model. there are 1, 2, 3, 4. There are 4 LSTM layers, and 1, 2, 3. There are 3 drop-off layers and 1 dense layers. The same 4 LSTM layers, 3 drop-off layers, and 1 dense layers. And this is the summary of the updated call parameters. LSTM layers has changed into 4, and the neurons in each LSTM has become 100. There are 3 drop-off layers. There's 30% data will be drop-off in drop-off layers. And the length of time sequence input sequence is 60. The bench size for training is 30. The number of echoes for training is 100. Then we began to use the revised model for our forecasting. Then we get 2 graphs. Still the graph, there are 3 curves. Okay, now we go to the part 5, compare network performance. Comparison between the original model and the revised model. Now we begin to compare the result of them. We can see from these 2 graphs, obviously the second graph, the second model have a better performance. You can see this curve is very close to the real value, and the error is smaller than this one. Then we compare the parameters of 2 models. Here we can see basically we increase all the numbers of the parameters. Then we got a better performance of the second model. So now from the previous work, I would like to see these are the factors that can contribute to the improvement of the performance. Increased LSTM layers, the increased drop-off the layers, the increased number of neurons per LSTM layers, the increased length of the time series input sequence, the increased bench size, the increased number of apertures. However, there's still a few parameters which effect couldn't be determined, such as percentage of test and the percentage to drop with drop-off layers. And like the first percentage of test, I did 2 models and got the result, then compare them. This the 2 graphs. It's difficult to see the detailed difference, so I think the further research will be needed to evaluate these parameters. Then we go to the part 6 project report. This is the introduction, my work, and what I have learned. First, we can access to the prediction problem in time series data happen in the real world. And we learned that the learning process of model can be different. Even for the same model in different time, it can predict a different result. And we hope to let the model work many times to get better performance. And third, we can improve the model performance.